again. This is Aaron Jerome Electronics. We're listening to Sweet Child of Mine by Guns N' Roses. This is a cover by the Baltic House Orchestra. I think it's abbreviated BHO. This was made for the Marvel movie Thor: Love and Thunder. Great music. Okay, getting to work now. It's time to get to work. So, we're learning about Boolean algebra and simplification. Let's talk about the history of this just a little bit. We have been using logic gates, and or not gates and so forth. We've been working with these gates and we've been working with these integrated circuits. These are all made from something called transistors. Transistors are switches. We can program what these switches do. Then they do their thing, usually to serve human needs. And after we program them to do what they're supposed to do, we can go off and forget about them or interact with them or whatever we want. The very first transistor was introduced to the world just before Christmas, 1947, and it was large. Today, we can put billions of transistors in a very tiny area. Groups of transistors work together, resulting in what we call artificial intelligence. So, in order to give meaning to clusters of transistors, that requires math. The math used to control the world's technology is known as Boolean logic. This is George Boole. He introduced to us the logic that we need to use with transistors. He wrote a book, An Investigation of the Laws of Thought on Which Are Founded the Mathematical Theories of Logic and Probabilities. He wrote this book back in 1854. That was nearly 100 years before the first transistor was introduced, so he was actually doing something that we really needed, but we had no idea that we'd be using the transistor to do it. Essentially, George Boole quantified mathematically how humans think. Today, we use his ideas to design artificial intelligence and automation and then emulate perfect human logic. His ideas enabled us to turn thought into an equation, which is what we've been doing pretty much since we started this class. By now you realize that the skill of simplifying is very important. Lucky for us, simplification is also pretty easy. Just takes a little practice and then you're pretty good at it. That's what we're going to discover now. So, this is just a quick review of what we've already learned. We've got a truth table here. We've got some input sensors and output Z. You might recall that the inputs really are just a binary count because all we're really trying to do is include every possible combination of input sensor results. The outputs are determined by your brilliance, genius, and your idea. And maybe after thinking about it, you've decided that you want the actuator of the automation to do its thing when the red ones appear on these particular rows. What this means is that we're going to pull a term from each one of these rows, only the rows that have ones. These lines down here, it's probably appropriate to think of those in this instance, while we're talking about min terms, as AND. So if we want to pull, and this line right here, that vertical line means equals. So we will pull an equation, or we'll pull a term out of each one of these rows, starting with row 1, which is there below row 0. Below A, let's back up, below A, on row 1 is a 0. So if you remember, we're going to call that not A because it's a 0 under sensor A. Remember the line there, that means AND, so we're going to put a little AND sign there, operator there, and the next term is, or the next variable is not B, and another and the next variable is C. It's not knotted, so it's just C. We've done all this. You're used to this. You're familiar with all of this. So I'm going to go quickly through the terms of the next rows. There they are. And then once we have all of these terms, we don't need the truth table anymore. We've got the terms. We want to combine these into an expression. To combine these, we're going to OR each row together. To complete the expression, that just means put a plus sign between each one of the terms. We're going to tighten it up a little bit and also point out that this equation will work for building simulations, but it is a breadboarding nightmare. It can be simplified, and simplification means a lot of work, a lot of things, meaning mainly less work for you, fewer parts, less expense, less time. We'll talk about more benefits of simplification in a minute, but remember that the multiplication dots are often implied, and that means they're optional, so I'm making them implied now. Simple sitting together without any sign between them means that there is an implied and between them. All right. Using special techniques, this expression can be reduced to this expression, so it can be simplified quite a bit. But you need some mad simplification skills. This is one of the major skills used by those who graduate, who work in the field of electrical and computing engineering. And it's not hard, just takes a little time to be able to do it, and it saves you a lot of work, makes it more efficient. Smaller expressions can do the same work as big ones, so we need to simplify. Here are a few of the benefits of reducing an expression. You use fewer parts. They're less complicated to breadboard. It takes less time. Parts cost less. Mass production costs less. They're easier to sell, they're easier to troubleshoot, and easier to repair. These are the tools that you can use to make your expression smaller. First, we're going to discuss the laws, and after that, we'll discuss the rules. These are the laws of Boolean algebra. Now, you have been exposed to all of these laws before. This is where the rubber meets the road. This is where the world actually uses these laws. But most of my students have been exposed to these laws probably since about 7th grade. We're going to be talking first about the commutative law. The commutative law means that variables can commute, but really that just means variables can be moved around without changing the value of the expression. So an example of that here in an addition law is that a plus b plus c, that's the same thing as b plus c plus a. We moved around, we commuted the variables, but on each side of the equation, those expressions have exactly the same value, even though we've moved things around. Symbols separated by plus or signs can be mixed around. In other words, 1 plus 0 plus 1 equals 0 plus 1 plus 1. They have the same value. In addition to addition, there's also multiplication. You can commute multiplication. A times B times C equals B times C times A. These two expressions have the same value. Symbols separated by multiplication or and signs can also be mixed around. In other words, 1 times 0 times 1 is equal to 0 times 1 times 1. They have the same value. On the other hand, mixing the operators doesn't work. You cannot commute mixed operator expressions. For example, A times B plus C does not necessarily have the same value as B plus C times A. So you got to be careful. If there are mixed operators, you cannot commute the expression. Expressions with mixed ands and ors should not be moved around. Okay? So that is the commutative law. Let's talk about the associative law. The associative law, here's an example of it. A plus B or C, or A plus B or C. Notice we have associated B and C by putting parentheses around them. And that's really all associating is putting parentheses around something, because by doing so, we're saying we want to focus on this part of the expression first. Well, we can move those parentheses. Parentheses are used to point to the math that maybe you should do first. Symbols are separated by a plus sign or signs, can be easily reassociated. Right here, we've got the equivalent Notice I have moved the parentheses around A and B, but the value of the expressions do not change. That's why the associative law is legal, and also why it is so valuable. We'll explain, we'll give demonstrations of why that's valuable in a minute or two. The same thing can be done with multiplication. A times B times C, where B times C has been given emphasis with parentheses, is equal to A times B, in parentheses, times C. It's the same. Notice again that the parentheses are used to the point of the math that you're going to do first. Symbols separated by and signs can be easily reassociated. So that means that parentheses can be moved around without changing the answer. That's really the bottom line. So we've talked about commutative, talked about the associative. Now with those two ideas in mind, hopefully your mind is also drawn to the third of those three laws that are commonly grouped together in algebra. That the third law is the distributive law, and it means that variables can be rearranged without changing the value of the expression. What do we mean by that? Well, we mean distribution and factoring, really. What we've got here, we're moving the variable a around. The a on the left is distributed. A times b plus a times c. That is, A is distributed to B and to C. It is equal to A being factored out from B plus C. So moving the variable A around can give greater focus to whatever we want to focus on, maybe in this case B plus C. The value on each side of the equals sign, the value of the two expressions is the same. So it can be done as well this way. This is a little bit different example of the distributive property. A plus B times C plus D. Maybe this is another example used as an extra variable, and you may have learned that these factors can be derived using the FOIL method. That is, A times C equals AC plus A times, or no, we did FOIL first, then outside. I've done the insides here, B times C. I'll do it the right way on further examples. But anyway, A times D, B times C, A times D, and B times D mean we have considered every possible combination of A, B, and C, D. Okay, so now what I'm doing here is I am giving you an example and hoping that you can look at it for a moment and identify which law is being applied here. Can you look at this and figure out which law is being applied? Well, the arrangement of A times B times C times D has not been changed. All we've done is put parentheses around things, so that is the associative law. This is the kind of thing you need to know for, tests, assessments, exams, quizzes, etc. Here's another one. What law is being applied here? Well, we've got two terms here, R plus S times T plus U. What we're doing is the FOIL method here. R plus not T is R not T, plus outsides, R times U is RU, plus insides, not S, times not T, plus the last, that's FOIL, not S, times U. So these are equivalent. We have just used the distributive law. Here's another one. What are we doing with this? Well, the terms are pretty much all the same on both sides of the equation, but they have been moved around. Well, moving things around, that's the commutative law. What's this one? Notice that each of the variables is in the same location. Things have not been moved around. This is not commutative. We haven't actually done any math, so it's not distributive. All we've done is put parentheses in different places. That makes this associative. What about this one? Well, in this case, we have multiplied the d times the not ot plus the d times the not, or the o not c. We've distributed that d. It's still got the same value on both sides of the equations, so that is a distributive example. Okay, so Boolean simplification, those were the laws. Now we need to talk about what we're calling the rules of Boolean simplification, and there's several kinds of rules. The AND rules, the OR rules, and there are some other rules as well that we'll talk about. But we're going to talk first about the AND rules. Okay, here is an AND gate. We're going to put variables, information from the sensors into this AND gate. We've got a 0 here. We're sure that we know one of these is a 0, but we don't know what the other input is, so we'll represent that by a variable. So what we want to know is, what is A times 0? What is that? What does this Boolean equation look like? I just stated it. We've got A, and we're going to multiply that, and we're going to multiply it by a 0, and what does that equal? Well, hopefully you know this is binary. It can only have two values for A, and we're going to try both. 1 times 0 is 0, and 0 times 0 is 0, so both end up as 0. This means that A times 0 is always 0, and that is an official rule of Boolean algebra. Now, I made it red, but I'm going to suggest that you don't write it down, because really it is so simple to remember that anything times 0 is 0 that I just don't think it's worth taking the time to write it down. Let's try another one. We got another AND gate because these are AND rules. And what we're going to do this time is use a 1 instead of a 0, but we still don't know the other variable. What happens to that? What does the Boolean equation look like for that? Well, that's A times 1 equals something we don't know, allegedly. But it's binary, so A can only have two values, 0 and 1. So 1 times 1 is 1, and 0 times 1 is 0. So both end up as whatever A was. This means that A times 1 is always A. A times 1 is always A. It's red. Don't write it down. It's obvious. Anything times 1 is what you started with. Let's try another one. This time we don't know either variable, but we know they're the same variable. What does the Boolean equation look like for this? A times A equals something we don't know, allegedly. Well, let's try that. Only has two variables, 0 and 1. So 1 times 1 is 1, and 0 times 0 is 0. Two of the same variable is the same as one variable. So this is called duplicates, and we're basically, if you have duplicates, eliminate them until you only have one, because the answer's the same, okay? That's another Boolean algebra rule, but really you don't need to write this down either, because when you see duplicates multiplied together, you can eliminate all but one of them and get the same answer. Let's do another one. This one, what if we only know that the second is the opposite of the first? So we got two variables here, but they're opposites of each other. What does this equation look like? Something like this. A times not A. A is binary. It only has two values, 0 and 1, but the second must be the opposite of the first. So 1 times 0 equals 0, and 0 times 1 equals 0. Whenever you see opposites multiplied together, 0 times 0 is always 0. That means whenever you see opposites together, there's a 0 in there, and anything times 0 is 0. That's another rule of Boolean algebra, but as long as you can remember that opposites cancel out, that's what you need to really remember. Those are the AND rules. Let's talk about some OR rules. You know what A plus 0 is, right? It's A. You don't need to write it down. It's pretty obvious. What is A plus 1? Oh, that's kind of tricky. Well, A plus 1 is 1. And I've explained this to my class before, explained it in other videos before, but some people still get confused. What if A is a 1? what if A is a 1? 1 plus 1 can't equal 1, can it? Corn apple, that is a allowed cuss word in my classroom because it's a fruit and a vegetable. But anyway, what the heck does this mean? Or, if either one of the inputs is true, then the output must be true. Another way to look at this is true plus true is true, and true plus nothing else is also true. And that's what you need to remember with OR gates, and the OR gate truth table is true plus true is true. So hopefully you remember that there. A plus A, that's 1 plus 1 or 0 plus 0, right? In other words, that is another example of duplicates, and if you have more than one variable added together, you can eliminate all but one, just like when they're multiplied. If you have duplicates, reduce it down to a single instance of that duplicate. What about opposites? Well, A plus 1, one of them has to be a 1, one has to be a 0, so it's always 1 plus 0 or 0 plus 1, which is always 1. So when you have opposite variables added together, the result must always be 1. Remember, multiplying them makes them go away, but adding opposites makes 1. So the AND rules, the OR rules, we've talked about all of the AND rules. You don't need to memorize them because they're intuitive. You can do them in your head. Well, at least there's not a lot to memorize. The OR rules, same thing. But there are a few other rules we need to talk about. I've already talked a little bit about double knots and how they cancel out, or even number of knots cancel out, odd number of knots reduced down to a single knot. I'll be talking about that more. But I do want to talk about a special rule called the consensus theorem. Red words, write it down. This is a hugely important shortcut when you're simplifying. In fact, this is probably the most often used shortcut when you're using simplification. The consensus theorem. Are you ready to write? Okay. With a consensus theorem, the definition of the consensus theorem is this. Anything, and we're going to call that a variable A, anything that is added to its own opposite, but that opposite is times by something else, then you can eliminate the opposite. Hopefully that makes sense. There is a long proof for this. That's why we use the shortcut. Someday I'm going to find where I put that long proof and maybe insert it into this video or someplace else. But for now, really, for the consensus theorem, all you really need to remember is that anything added to its opposite times anything else, you can eliminate the opposite. I will show you several examples of this. Okay? Again, the consensus theorem. This is a shortcut that we use, saves us a ton of time and work and expense, gives us better efficiency. Anything added to its opposite times anything else, eliminate the opposite. You got to memorize the consensus theorem. Okay? So this equation equals the same as this equation. Just want to make sure that that is absolutely clear. Okay? Now, these are all the rules we've gone through, except we have not talked about 14, 15, and 16. I used to actually give this to students. You can take a picture of it if you want, I suppose, but really, all the multiplication rules are intuitive. All of the addition rules are intuitive. You know the double knots cancel out. We have just talked about the commutative law, the associative law, the distributive law. You don't need to memorize them. You just need to practice them a few times. We've talked about the consensus theorem, which is anything added to its opposite times anything else, you can kill the opposite. 13, A, B, C, and D are nothing more than examples of the consensus theorem. Anything added to its opposite times anything else, you eliminate the opposite. Anything added to its opposites is multiplied by anything else, you can eliminate the opposite. Anything added to its opposite times anything else, you can eliminate the opposite. Anything added to its opposite times anything else, you can eliminate the opposite. They are just different examples of the same thing. We are going to be talking about De Morgan's law more often, but I've already explained this as change the line, change the sign. We will be getting to that more later. There is a shortcut rule for 15, which takes about as much time as just doing it the regular algebraic way. This rule is, well, it can save time. Rule 16 can also save time, but really it's just factoring and simplifying. And you don't, I hardly ever see this pattern enough to even remember it, because it's just quicker to just simplify it one step at a time. So this is just a summary of all of Boolean's and De Morgan's theorems and laws, just making sure you have them. Now it's time to practice. Let's try one. Let's take this circuit, this simulated circuit that we might have made in Multisim. What we want to do is pull out the unsimplified equation from this. Now, my students have this pre-printed sheet so that they can pull out this unsimplified equation. The idea is, since you already know how to do this, and since you learn better by doing it faster than me, you or my students should be halfway done with this already, even though I'm going to give the answers. See if you can pull the equation, the unsimplified, don't try to simplify it, give the unsimplified equation before I give it to you. You can even pause the video now if you need to. But here I go. Going into that first AND gate, we're going to simplify it in a minute, but going into that first AND gate is an A and a B. Well, that's an AND gate. It multiplies. What comes out of a multiplied A and B? Well, it's A and B. We are putting a C into the lower input of that OR gate. And what does it look like when you OR A and B to C? Well, that's just AB plus C, right? All right. So now B is just about to go through a NOT gate inverter. When it comes out, it's a NOT B. And then we have to multiply this AB plus C times NOT B. Now, the upper term, well, it's not really a term. The upper expression needs to have an association. We're going to apply the law of association here by putting parentheses around that to preserve the parenthetical relationship when we multiply by B, because B or not B must be multiplied by everything in that upper grouping. Okay, so that is what it looks like when you combine AB plus C with and multiply it with not B. All right, going into the bottom of that OR gate is a copy of A, and we're going to add that to our expression, and it should look like that. All right. The bottom AND gate has an A going into it and a B. We're going to multiply those together, which means what we've got is A and not B. Next, we need to add that to the expression that we've already built above. And of course, that means we've restate that equation built above and then add A not B. There it is. There's our equation. Now we're going to simplify it using the rules and laws that we just learned above. I'm just restating it here, and I'm saying probably the first thing we should do is distribute that B into the parentheses. So I'm going to distribute the not B in. Now, I'm pausing here because I'm hoping that you students remember, and if you don't remember, this is your reminder. If you will pause this and try to simplify this equation before I show you the answer, you will not only prove that you understand what we're talking about, but we will get beyond just pretending that we're learning by doing monkey see, monkey do, recording the answers. But I do want to point out here that every time I list this equation in a different version, it's called a different iteration. And if you need me to help you troubleshoot, you need to list your iterations. We complete this simplification one iteration at a time. As you begin, don't try to do a whole bunch of things at once, because that's a surefire way to make sure that you get it wrong. So, hopefully you've paused it by now. If not, do it now. And now I'm going to show you the answer. So to distribute this, I'm going to put not B with AB. So it's AB, not B. And I've got to put that not B with C as well. And that's what I get. That's my result. Okay? So now all I've done is removed the parentheses because we don't need to preserve the parenthetical relationship anymore. But now I'm going to focus on that first term, the A, B, not B. A times B times not B. Hopefully you've noticed that term and realized that anything times its opposite is a 0. So the B times the not B is a 0, and that means you've also got a 0 times an A, which means that entire term can be eliminated, and that's what it should look like after you've eliminated the entire term. Now it looks like I've decided to focus on I put parentheses around the last two terms. That's all I've done. I have associated the last two terms because I'm going to focus on those A's, which means I am going to factor them out of there. So, factoring A out, doing that, what I've got is A with a 1 plus a not B inside the parentheses. Now that 1 there, we call that a placeholder. If you look up above in the previous iteration, we've got an A plus A not B. And that first A there, if we multiply that by 1, we would still have an A, and we probably wouldn't show the 1. But if we ever needed to redistribute that A back into that associated term inside the parentheses, we would need a placeholder there, which is why we left the 1 there. Otherwise, if you try to go backwards and you don't have that 1 there, you get a wrong answer. So that's why the 1 is there. Hopefully that's understandable. We also need to realize that 1 plus anything is a 1. Do you remember that? 1 plus anything, 1 plus 0 is 1, 1 plus 1 is 1. True plus true is true. Okay? So that 1 plus the not B is just a 1. Okay? And hopefully you were able to figure that out before I showed you. The next thing I'm going to focus on is 1 times A. 1 times A, that's just A. 1 times A is A. 1 times anything is just whatever you started with. Okay? So, sometimes as a final step, I will alphabetize, which means I will commute the equation. And the reason I do that is because sometimes on tests you are given multiple choice answers which don't include the one that you see there, F equals C not B plus A. It might be commuted. So I'm just putting it in alphabetical order to show that it can be commuted. The value is still the same, but that is the simplification. At this point, I also ask my students, which would you rather breadboard? The top equation? No, that's a breadboarding nightmare. Or the bottom equation? That one is doable, and it is much more efficient. Let's do another one. I want you to pull the unsimplified equation out of this one. Hopefully you have a worksheet. I know my students do. And pull the unsimplified equation out of this. You might want to pause the video now while you do that, and then start it back up in a moment. Okay, here is how this is done. There's a copy of A going into a NOT gate. It comes out as a knotted A and goes into the first AND gate. Then there's a copy of B going into the second AND gate, which incidentally is nested to the first AND gate, and so what we have made is a triple input AND gate as discussed in earlier videos. We have a C going into a NOT gate. It becomes a NOT C, and so we have B times NOT C. That results in B NOT C. And when we multiply that with NOT A, we get NOT A times B, not C. Going to the next one, we have an A going into the first AND gate, a B going into the second AND gate. They are again nested, and that means we have a triple input AND gate, and we have in the lower input of the AND gate A not C. B times not C is B not C. A times B not C is A B not C. The bottom triple or the bottom nested AND grouping has an A, a B, and a C. None of them are knotted. Multiplying them all together will give us A, B, C. Now all we have to do, we have a nested OR grouping here, so that's a triple input OR gate really, and we're just ORing everything together, and our equation is not AB not C plus AB not C plus ABC. Next thing we want to do is simplify this. So if you're feeling like you are understanding how to simplify things, you might want to pause the video now and see if you can simplify this, and then compare your answer to somebody else's, your nearest neighbor, or compare your answer to the answer that I am going to give. Okay, so pause the video. All right, here's the answer. First of all, we're going to associate useful terms. To do that, we want to look at the terms. The first term has a not A, the second two don't. The first term has a B, the second one has a B, the third one has a B. If we wanted to, we could factor out a B with all three terms. But that's a little too complicated for starting, so to start out when we simplify, I generally will associate two terms instead of three to keep things simpler. Let's see, a not C in the first term, a not C in the second term, and a C in the third. Let's go ahead and associate the first two terms. Now, what we want to do is pull out or factor out everything from this association that is the same. Because if it's not the same, it'll be opposite, and we want to leave the opposites because opposites can be canceled out. What's the same in this term? B, not C. So we're going to factor out B, not C. We pulled B, not C out. We have remaining within the associated terms and not A and an A. Hopefully you remember that anything added to its opposite is still a 1. So, so we've got B, not C times 1 plus ABC. Well, we remember that anything times 1 equals 1. That means that 1 can be eliminated. And that's our next iteration. Are we done? Probably not. Is there anything that's the same in both terms? Yeah, there's a B that's the same in both terms. So we're going to associate these two terms, and we're going to factor out a B. And what we've got left is not C plus AC. What do you do with this? Well, first of all, you don't have to, but it sure helps. I'm going to commute or move things within the associated terms around to make it a little easier to understand what I'm going to do next. All I've done is swapped around the C and the A. Doesn't change the value. A times C is the same as C times A. But what this does do is make it easier to see the consensus theorem. Do you remember the consensus theorem? The consensus theorem is anything that is added to its opposite times anything else, you can eliminate the opposite. So that's what I'm doing. I'm going to eliminate that C right there. And let's see what I've got left. I've got left the not C plus A. Now I'm going to redistribute that B back in. So I've got B not C plus B A. I didn't need that last parenthesis. And that is pretty much my final answer, except that I might alphabetize it to make it a little easier to see on test questions and so forth. So now you've done two problems. These have been fairly difficult problems to start with, but I think you understand a lot from doing them, mostly because, hopefully because, you have tried to do them yourself before you looked at my answer. Because you probably, if you just wrote things down as I gave the answers, that was called monkey see, monkey do. There's a good chance you didn't learn anything. Try doing these on your own, and then when you get stuck, look at what I've done to get past where you were stuck and to answer your question. You learn so much more when the answer or when the question has already been installed in your mind. You learn so much more if you look for an answer with a question that's already been installed in your mind. Okay, let's go to the next one. Let's simplify this one. Pause the video. Okay, back to work. I'm going to associate both of these so that I can factor out one of them. We always factor out the thing that's the same, leaving what is in what's left as opposites. So I pulled out the G, and now the H's are opposites, and any variable plus an opposite is a 1. Hopefully you remembered that. 0 plus 1 equals 1. Okay, and then hopefully you've remembered that G times 1 equals G. Okay, so that's your answer. Let's do another one. Might want to pause the video now. Okay, the consensus theorem, we're going to use that, the consensus theorem, and what does that mean? A consensus means we're going to eliminate a variable. See, anything added to its opposite times anything else, you can eliminate the opposite. That's why the J is red. And so I'm going to rewrite a new iteration where the J is gone. Next, I'm going to distribute, meaning I'm going to multiply the J that's on the outside of the parentheses by everything within the parentheses. Okay? That's what I'm doing here. So I get J not J plus JK. Hopefully you remembered that anything multiplied by its opposite is always 0. Why? Because one of them has to be a 1. The opposite is the opposite. It's the 0. Or it's a 0 times a 1. Either way, it's 0 times something, and that is always a 0, which means that whole term can go away, and we're left with JK. All right, try this one. Pause your video. First thing we're going to do is make an association, and really it doesn't matter which two you associated first. If you've done it right, you should get the correct answer. I am going to associate the first two terms just because I've looked at them and I see there are sames and there are opposites in there. You pull the sames to the outside and you leave the opposites on the inside and see if there's anything you can do with them. I've decided the sames are M, not M and N, so I've pulled them out. What's left are the opposites, L plus not L, the opposites. And then I had to tack on in this iteration to make it equal the plus not L, M, N. Hopefully you remembered that anything added to its opposite is always a 1, and anything multiplied by 1 is just what you started with. Next, I'm going to associate these again, because there's possibly something in there that I can pull out, pulling the sames out, leaving the opposites in. I've decided that I'm going to factor out an M, leaving in an L, or a not N, and a not L, and an N. I hope you have noticed that this is a consensus theorem candidate, but if you don't see that, it may be because we need to commute first. I've traded places with the N and the L, and now hopefully you can see the consensus theorem a little easier. That means anything added to its opposite times anything else, you can kill the opposite. Okay, so now I'm going to distribute that M back in, and that gives us the final answer. M times not N plus m times not L. And that's as far as we can go, because if we factored the m back out, we'd get the iteration above the answer here. And there's nothing you can do with variables that have different names. You just don't know what they are. Okay, let's do this one. Pause the video, see what you can get, and then restart. Okay, with this equation, we're just reminding ourselves that q plus not q, I should have a not above that. I don't. Maybe next time I edit this video, I'll put the not in there. But q added to its opposite, which is shown in the iteration above, is always a 1. And 1 times anything else is just the anything else. So 1 times a equals a. So we're just saying that, you know what, we got the p and the q plus p not q plus p not qr. Now these are pre-associated, and we need to pull sames out and leave opposites. The only thing that's the same in both of those is the p. So I'm going to factor the, oh no, it's the p and the not q. I fooled myself. So the only thing that's the same in there is the p and the not q. We're going to factor those out. Remember, we need a placeholder for when we factor something out and there's nothing left there. And so we're putting the 1 in as the placeholder. And 1, if you remember, 1 plus anything is still a 1. So I'm going to demonstrate that in the next iteration. And then I remember that 1 times anything, that makes the 1 go away. Or it is implied, really. But we now have simplified this down to p not q, which is much simpler to breadboard than the original equation at the top of the iteration stack. Okay, so hopefully that made sense. Let's try another one. You'll want to pause the video and see what you can do with this one. Okay. So this one is a FOIL factor, meaning we're going to multiply everything in the first association with everything in the next association. We're going to be using FOIL to do it. So what we're going to do is multiply the first terms. That results as s times s. And we're going to add that to the outside terms multiplied together. That means we're going to add an st. Then, according to the FOIL mnemonic, we're going to multiply the inside terms, which is a not ts, add that to the grouping. And then L for FOIL, L means last. We're going to multiply the last two terms. We've got not t times t. Next, we're going to look for the, we're going to notice the duplicates. The SS, those are duplicates. If we have duplicates, we can always replace that with a single copy, no matter how many duplicates there are. In the last term, we have got t times not t. One of those has to be 1, one has to be 0, and 0 times anything is 0, which means we can eliminate that term completely, which is what I'm doing here. Now, all three of these terms have an s in it. I think you're probably ready for us to factor the s out of 3 terms instead of 2. And what we've got here is a 1 placeholder plus a t plus its opposite not t. We can actually look at this 2 ways. Anything added to its opposite is a 1, but 1 plus anything is a 1 as well. So really, it all comes down to it's all just a 1. And 1 times s is really just s, and we done. And it's so much simpler to, well, wire up a circuit where it's always on, as opposed to wiring it up above with the above complications. Here's another one. It's getting a little harder. Let's see if you can do that one. Pause the video. See if you can figure out your way through this one. Okay, back to work. Distribute B. What does that mean? Well, that term there, B times C or D, we're just going to distribute the B into that, and we end up with BC plus BD. We can do the same thing with the last term. I just didn't want to do them all at once. I wanted to keep them in separate iterations so we didn't get confused and mess up somewhere. So not C times C plus not C E. Now we've got that iteration complete. What are we going to do next? I'm looking at this. I'm seeing a lot of B terms. I am seeing a lot of C's. I think what I'll do is I will search for duplicate terms, and maybe before I can actually see duplicate terms, I might need to rearrange, but that's not true this time. I have BC plus BC. Those are duplicate terms. They are exactly the same thing, so we can eliminate one of them, and that's our next iteration. Now, I'm also going to look for opposites. In this term, I've got not C combined with a C, and those are opposites. One of those has to be a 1, one of those has to be a 0. 0 times something is just 0. That entire term can go away, and we're left with this. Now, we acknowledge here that the work is done. We cannot simplify this any further. It just cannot be done, because if we pulled the B's out, we would be trying to simplify using a C and a D. So, and we cannot pull anything else out. This term is as simplified as it's going to get. Let's try another one. Let's simplify this one. This one I think is kind of a fun one. Pause the video, see if you can figure it out. Okay, back to work. What I'm going to do first is I'm going to apply the consensus theorem twice. Anything added to its opposite times anything else, you can eliminate the thing that's multiplied by something else. So I've got B plus not BC. I've got not B plus BC. Anything added to its opposite times anything else, you can eliminate the opposite that's multiplied by something else. There is my next iteration. If you look closely, you can see that there are duplicates in this iteration, and whenever there are duplicates, you can reduce them to one copy. We've got redundant copies, so if we take one of those copies and eliminate it, we come up with this, and it is the same value as the previous equation. Now, probably what you're seeing is FOIL factor. We're going to have to FOIL factor these, so we've got B times B as the first, B times C as the inside. Is that right? No, the outside. B times C is the outside. The inside is B times not C, and the last two terms are C times C. And we need to look for opposites again when we do this, and we do have opposites. There's B times not B. One of those is a 0, so we're going to have to eliminate that whole term. Also, we've got duplicates with the C's, so we're going to eliminate one of those duplicates, but not both. And that is still the same equation. Maybe we're not done yet. Can we do anything else? Yes, I think we can. Each one of those terms has a C, and there are opposites. So we're going to factor a C out of everything. And now we have B plus not B plus placeholder 1. Well, 1 times anything is 1, so the quick way to look at this is that everything in the parentheses is just 1, but B plus not B is also a 1, and 1 plus 1 is 1. It's all just a 1. 1 plus, that should say 1 plus anything is a 1. I guess not got another edit for the future. 1 plus anything is just 1, and C times 1 is just C. Which one would you brother breadboard? The top one or the bottom one? Here's another one. Let's try this one. Pause the video. Okay, let's get to work. First thing I'm going to do is I'm going to commute that, move things around so that I can see duplicates a little easier. If you can see duplicates without commuting, make sure you eliminate one of them. Our next iteration looks like this. Now, I think probably the next thing we need to do is distribute that X into the parentheses. So I am doing that now, and this is normally where students would stop. This is just about as simple as you can make this. However, I'm going to exhaustively simplify this, showing you that it can be simplified further. I might go back to this concept a little later. You don't have to learn this one, but I know that there are students who are curious. There are people out there curious to know how in the world would you simplify this even further. So pay attention or go to sleep or speed fast past it if you want, but here is the long way to simplify this even more. The idea is to multiply that middle term times 1. Why would we do such a thing? Well, it's because we can exchange that 1 for another way to say a 1, which is W plus not W. Why specifically W plus not W? Well, that first term has a W in it, and the last term has a not W in it, and so we can operate if the middle term had W's in it. So next thing I'm going to do, so I'm just saying the variables were strategically selected to match the outer terms. So what I'm going to do now is distribute the X and the not V into the parentheses. There we go. And this, I think I'm associating this last term, so I'm pulling out, after I've associated the last two terms, I'm pulling out the X not W. And I have to use a placeholder 1, but now I've got 1 plus something. 1 plus a V, 1 plus anything is 1, and 1 times anything is what you started with. And now I've simplified it down to, well, it's still a little bit bigger than the normal stop location, but we can, I'm going to continue on the other side here, we can also associate the first two terms. We can pull a W out of those first two terms, leaving inside the associated group a V plus X not V. I have commuted those so it looks more like something I can use a consensus theorem with. But if you can see the consensus theorem without commuting, that's just as well. V times not V. Anything added to its opposite times anything else means you can kill the opposite, which is what I have just done. Okay, now I'm going to redistribute that W back in, and now I have WV plus WX plus not X not W. Now that is very similar to the normal stop, but not exactly similar to the normal stop. What I'm going to do now is associate the final two terms because I can see a W that's an opposite, and then I can see the X's are the sames. So I'm going to pull that X out there. I've got the opposite terms there. Anything added to its opposite is a 1, and 1 times anything is just the anything. And that is how you do the further simplification, by adding a 1. Now, I should point out that this simplification is much easier, takes many fewer steps to get to this final simplification. And I'll teach you how to do that probably in the next video when I talk about De Morgan's theorem a little bit more. We've talked about that a little bit with change the line, change the sign, but we're going to talk about it a little bit more. Okay, so now here's some more simplifications, but these are easier simplifications. Pause the video, see if you can get them real quick. Okay, back to work. We're going to use the commutative law so that we keep all of the variables that are the same symbol. We're going to put them all together. Haven't changed the value, but we've just put the same things together. Now, hopefully you remember that anytime you have duplicates, whether they're multiplied or added, you can eliminate them. And we got lots of duplicates here, so I'm going to eliminate my duplicates. They look like this. Now notice everything here is multiplied by 1, and anything times 1 is what you started with, so that is our resulting simplification. Let's try another one. Pause the video. Okay, so what I'm going to do is the same thing I did with the last one. I'm going to commute, which means I'm going to put all of the variables with the same symbol next to each other, and then I'm going to eliminate them, and what I've got left is something multiplied by 0. We probably could have skipped these steps and just realized everything's multiplied by 0, which means x is 0 all the time. Here's another one. See if you can figure this one out. Pause the video. Okay, remembering that a times a is a, we've got some duplicates there we're going to eliminate. Now we've eliminated all of the duplicates. Now, I have noticed that there are two identical terms here, but they don't look identical until we commute them, and now they're commuted. We've moved stuff around. Now we can see that there are duplicate terms. So now, if they're duplicates, we can eliminate one of them, and this is our final result. No, it's not, because we've still got to commute these. Oh, and look, we've got... well, I talked about it as a Rule 15 before. Anything added to itself times anything else, you can kill everything. But you can also do it by pulling a C out of both of these terms, and then inside is going to be a placeholder 1 added to the BD, which will resolve down to a 1, and then 1 times C is just C. So whether you use the Rule 15 shortcut shown here or the version I explained where you use a placeholder 1, you get C equals X. Here's another one. Try this one. Pause the video. Okay, here we've got duplicates. We've eliminated a duplicate. But you need to remember that anything added to 1, and both of those things are added to 1, is just a 1. Maybe you've done that already. Great job if you got this. Here's another one. Try this one. Pause the video. Okay, I am showing a Rule 15 to kind of remind you of that, but you don't need it. You could factor out a C from the first term, and that would give you a placeholder 1 plus B, which is just a 1, because 1 plus anything is 1, and then you would multiply that by what you pulled out, a C, and whether you use C, whether you use shortcut 15, which is A plus AB equals A, or the long way, which I described, you should get the same thing. Now, in the second grouping, you have a consensus theorem. You might need to rearrange to see that it is anything added to its opposite times anything else. You can eliminate the opposite. That is C added to its opposite, not C times B. You can eliminate the not C. Dropping the parentheses, I can see I've got duplicate C's. And that means I can eliminate one of them. And then there's my final answer. Here's another one. Pause the video. Okay, here I'm going to use the commutative. It looks commutative? No, it's not the commutative. It's the, here I'm going to use the consensus theorem twice. Anything added to its opposite times anything else. Actually, we're just going to use that on the first one. On the C, there you see there's a not CD plus D. That is a Rule 15, which means it's just D. Anything added to itself times anything else, you can eliminate both. But again, explaining it the long way, you can put that not CD plus D in parentheses. Factor out a D, leaving a placeholder which is a 1. 1 plus not C, 1 plus anything is 1. 1 times D is D, and that gives us the result Oh, I'm commuting so you can see it a little better. And then I'm using the rule 15, and then we're done. All right, this one's going to take a little more time, maybe. Pause the video. Okay, how's this one done? Probably the first thing to do is realize there are duplicates there. Those first two terms, not A, B, C, D, plus not A, B, C, D, those are duplicates. We can eliminate one of them, giving us this iteration here. I guess what I'm going to do next is look at them and see, do I have sames in terms? Do I have different in terms? I think I'm going to look at those first two terms. There's a not A. I could pull that out of both terms, and I could pull the C and the D out of both terms. I think I'll do that, leaving the B inside the parentheses. And anytime you add opposites, you're going to end up with 1, and 1 times 1 is 1, or anything times anything added to its opposite is 1. I said times. I meant anything added to its opposite is 1, and anything multiplied by 1 means that you can imply the 1, which means it kind of goes away. Now we've got two terms here. What do we do with these? Well, the A's are opposites. They should be left inside the parentheses. The C's are opposites. Maybe those should be left inside the parentheses. The D's are the same. We can pull those out. Can we do anything with this? That's the last slide. Evidently, we cannot do anything with this unless maybe we can do that and multiply by one thing. But that's as far as I think we can go. I'm looking at that. If I pulled out the A, I can't pull out the A. I can't pull out the C. There is no B in both terms, and I've got a D. If I pull the D out, I've got not AC times A not C, A, B, not C. You've got to be careful. Those are not, there is no opposite terms in there as a result. So that is indeed the final solution. Okay, that's the end of the introduction to simplification. Hopefully you are good at it by now. Thanks for watching. Aaron Jerome at Jerome Electronics. See you next time.